So now we start a new chapter, which is about tangent spaces and singular and non-singular points. So and smooth points. So this is so like in differential geometry, an algebraic variety has a tangent space at every point, and so if the dimension of this tangent space happens to be equal to the dimension of the variety, then this is called a non-singular point, and if all the points are non-singular, then it's a non-singular variety, and over the complex numbers, non-singular varieties would be also complex manifolds, so like in differential geometry. It's not completely obvious from the definition, but it is the case. And so in the tangent space is some kind of vector space which best approximates the variety near the point. In fact, in the case that you have a fine variety, and say the point that you're looking at is the origin, you just can take the zero set of all the linear parts of the equation, of the equations of the variety that gives you the tangent space. And the way it will be is that the dimension of the tangent space is always bigger or equal to that of the variety, and if it's equal, then it's non-singular. So somehow it means, yeah. Okay, and so let me introduce this. So, so first we deal with hypersurfaces, which is the easiest case. Zero set of some polynomial in An. So let me just, for that, I don't even really have to talk about tangent spaces, so definition. So if f is a polynomial, we have these partial derivatives. Which are also there for polynomials. And so if x is equal to the zero set some polynomial in An, f this polynomial in kx1 xn, so hypersurface. And I assume that the ideal of x is just the ideal generated by f. So this just means that, you know, the ideal generated by x is the ideal generated by the radical of it is a radical of some ideal whose zero set it is. So this will mean that, you know, in theory, if x is zero set of some polynomial, it could be that this polynomial is a power of some polynomial, and it's actually the zero set of the thing of which it's a power. And here you just take the thing, you know. So instead of taking f to the n, you take f. Okay. So the point P in X is called a singular point, if all these partial derivatives are 0. Otherwise, it's a non-singular or smooth point. Okay. And I will usually, when this comes, so I will normally call X-reg set of, one also sometimes says regular for non-singular, so a set of non-singular points. And X sim set of all P and X. P is sim. And if X-reg is equal to X, we say X is non-singular also. So, okay, so this is extremely simple definition for hypersurfaces. Look at some examples. So, as I already said, we need that the idea of X is F, not just that X is the zero set of F. For instance, if I take X to be the zero set of y squared in E2, then obviously this is also equal to the zero set of y, which is, you will see, and you can see from the definition that this is non-singular, because always one of the derivatives is 1. But if I take this equation instead, I have d y squared by dx p equal to d y squared dy 0 for dx. So we certainly need this. One very stupid thing that for some reason I always see, so when one talks about singular and non-singular points of a variety, obviously points have to be on the variety. So I very often find in exams some answer where people say, you know, this is a singular point, but it actually does not lie on the variety. So then you know, that's, you know, the first thing to check. You know. So okay, then second, if I take the zero set of y minus x squared, then this is non-singular, because d by. So what are the derivatives? D by, because d by dy is always 1. And so it will be non-singular everywhere. If, on the other hand, if we look at the nodal cubic, so it would be like this. So as I said, a picture would be something like this, and this is the point 0, 0. And you can imagine that something special happens here, and if you compute the derivatives at all the points on x, there will always be one partial derivative which is non-zero, except at this point, obviously at the point 0, 0, all partial derivatives are 0. So the only singular point is 0, 0. I mean, corresponding to the equation that this is the only point where this is not a manifold. And the same for the Caspary cubic. would be the zero set of y squared minus x to the 3, and at least the real picture is something like that. And again, this is the point 0, 0. Okay. So this is all quite elementary. Now let's so in these examples we all see that there are I mean, in this case there's at most one singular point, but at least on such a curve we have only finitely many singular points. So we want to see that every variety the singular points are so in this case by the hypersurface the singular points are a closed proper subset. So there's an open subset on which the variety is smooth. This is the following proposition. So let X in N be an irreducible hypersurface. Actually, don't even can say. So, in principle, for this, we don't need it to be irreducible, but we just take the zero set of a polynomial, which is not necessarily a variety, it's an algebraic set, and we can talk about where it's singular and non-singular. So then the set of regular points is an open dense subset. So, prove it. So for simplicity, I assume that the characteristic is here.
Sorry, can I borrow you for the
What?
this pointer?
Yeah, certainly.
Thank you. I need it.
Okay. Yeah, I think normally at this time they use this. Okay. So, so this is, one can, as usual, one can somehow be a little bit more careful and remove this assumption. But here we just have, if you have a polynomial, all of these partial derivatives are 0, then it is constant. This is so let f be our polynomial such that irreducible with 0 sets x. So then we can describe the singular set. What is this? This is the set of all points in X such that f is 0, which means we are on X, and the partial derivatives, all the partial derivatives are 0, so that it's singular. This is just the 0 set of f df by dx1, because the partial derivative is also polynomial, until df by dxn. And this obviously is a closed subset of X. And now we have to see, so therefore x reg is open in X. Now we have to see that x reg is non-empty. Because if we have a non-empty open subset, it is dense. So if the track was empty, so then for all I, df by dxi vanishes on x, which is the set of f. And f is, as f is irreducible, we have that the ideal of x is equal to ideal generated by f. So that means df by dxi lies in the ideal generated by f. For all I. But as you can see, the degree of df by dxi is smaller than that of f. So it can only be a multiple of f if if it is 0. So that means all partial derivatives. So as the degree of df by dxi is strictly smaller than the degree of f, it follows df by dxi is equal to 0 for I. And now if we are in characteristic 0, if all partial derivatives vanish, the function is constant. If one is in characteristic P, it's a bit more complicated because you cannot deduce from the fact that the partial derivatives are 0 that the function is constant, because it could be a polynomial in the xi to the p. And then you have to work a bit harder to see that that cannot happen. Maybe, so by the way, can make this as an exercise. So let f equal to g times h. Irreducible, say. So I take 0. So obviously we know then that the 0 set of f is just the union of the 0 set of g times the 0 set of h, and in fact these are the irreducible components, union. And one should show that all the points in the intersection are singular. Okay, you can, that is quite, and you can try to show that. You know, it's quite easy to just write down what you have. In fact, what is more complicated is that, well, anyway, that if you have an algebraic set in AN, which has several components, and all the points which are on the section of at least two components are singular, so not just hypersurfaces, but this is more difficult. So now so this was the case of hypersurfaces, which is kind of easy. Now let's look at, more generally, at fine algebraic sets. So, and I also want to talk about the tangent set. So let X in AN be in a fine algebraic set. I don't necessarily need reducible. Definition. First I want to define the tangent space. So first I will talk about the differential of the polynomial, and then the tangent space will be defined by the differentials of the polynomials defining x. So let f in k1 n be a polynomial, and p point p1 to pn point in an. So the differential of f fp is just, I think, what you know. So this, I write it when I want to. So it's d f p, which is equal to the sum I equals 1 to n, the partial derivative at p times xi. So it's a polynomial of degree 1, which can be written like this. It's a linear form. I just take the partial derivatives times xi. So one can compute that we have the Leibniz rule. If I take this thing for the product of two polynomials, so maybe I write it like this. This is equal to the differential of f times g of p plus f of p times the differential of p h. So this is a direct computation. And the tangent space of x, so x was our prime variety at p, will be just is tp x, which is the zero set of all these differentials, where f runs to all elements in the ideal of x. So I take the common zero set of the differentials of all functions which lie in the ideal. So you can easily see that if we look at the case of hypersurfaces that we are looking before, so we had defined what the singular point is. We had said that p, so x is the set of f, and we have that p is a singular point. So this was, if if and only if all partial derivatives are 0, which means if and only if the differential of f is 0, and the elements here are multiples of f, so the differential of this will also be 0. So this means p is a singular point if and only if the tangent space is equal to the whole of AN. Okay? So, in general, we will want to say, so this was, and how does this generalize to general fine algebraic set? We say a point P in X is non-singular if the dimension of the tangent space P in X is equal to the dimension of X, otherwise it's equal singular. And this is compatible with what is written here. Well, one would have to see that at least we can see that for a singular point the dimension is too large, because this has dimension n minus 1 and this has dimension n. And here the dimension of the tangent space, you can take either the dimension as a vector space or the dimension as a variety, because it's just the zero set of some linear equation. So it's isomorphic to some affine space of some dimension. So its dimension as a vector space is equal to its dimension as a variety. Okay. Okay. So I should maybe remark that one can also see this slightly different. I mean, here I've written down the differential by this explicit formula. You can also view it differently, which maybe explains better what it is about. It's some kind of linear approximation. So for the polynomial f in kx1 per xn, and p in an, we have that if I take dpf, this is just the same as taking f of so I write p again as p1 to pn. So I shift it by the point p, and I take its part of degree 1. So it has a decomposition into homogeneous components. I take the degree 1 part of the polynomial, then the differential is just this. So in particular, for instance, if the point is 0, the differential at 0 is just the degree 1 part of the polynomial. And so you could also say that, so thus the tangent space of X is just the zero set of, I could just write I just write formally like this, I of X minus P1, which means the zero set of all the f of x minus p, so where x minus p stands for x1 minus p1 up to xn minus pn, 1 with f is in I of x. So you see, the tangent space is just, so you can really see it's a linear approximation. We just replace all the polynomials that define our x by their linear part, and we get the tangent space. Yeah, so I maybe should say, here I didn't say it quite correctly. Here I said the point P in X is non-singular if the dimension of the tangent space is equal to the dimension of X. But I would want to say it's equal to the dimension of X at P, where the dimension is equal to the maximum of the dimensions of the components of X, of the irreducible components passing through P. Okay. So this will not concern us very much because we mostly restrict ourselves to irreducible varieties. So then, anyway, it's just the dimension of X. But you can imagine that if you have, so if your variety looks like this, then this would be a non-singular point, and this would also be a non-singular point. Here it has dimension 2, it has dimension 1, but it's still non-singular on its component, and so we call it non-singular, whereas this point will be singular. Okay, but as I said, we will most of the time restrict our attention to the case that X is irreducible, then there is no problem. And then in this context, it is true, so one can show but that requires some algebra that, so if X in the end is reducible and P in X lies on at least two irreducible components, then it follows that P is a singular point of X. It's not quite obvious why this should be true, and I'm not going to prove it, but anyway, this happens to be the case. So for instance, in this intersection point, the dimension of the tangent space will be at least 3. Okay, so far to that. Now, if you look at the definition, it's not particularly useful because you take the common zero sets of all the differentials of all the elements in the ideal of X. These are very many polynomials, so one would not be actually able to check that for these infinitely many polynomials. But you can instead just choose a set of generators of the ideal. So this is following whatever I call corollary, although there's no theorem. So if the ideal of X is the ideal generated by some polynomials, then the tangent space P in X, or P is in X, is equal just to the zero set of these differentials of the generators. But careful, it is not enough that the zero set of X is equal to the zero set of F1 to Fr. You have to have that the ideal is generated by it. We have already seen this in the case when we have only one element. No? So we really need not just so let's prove this little thing. It's, if you wish, a corollary to the definition of the differential, or to the Leibniz formula. So clearly we have that the tangent space of X is contained in the zero set of dp f1 until dp fr, because the tangent space was defined as the common zero sets of all the dpf, where f is in the ideal of X, and these fi are. So on this side we only take more conditions, the zero set of more things. So we have to show the other inclusion. So let H be an element in the ideal of X, so we can write it as some Hi Fi in the ideal of X. Then what is dpH? We can apply the Leibniz rule. This is some I equals 1 to R, say Hi of P times dp of I, plus dpHI times fi of P. Okay, but P is a point in X. So therefore, fi of P is equal to 0. So therefore you see that dpH lies in, if you wish, in the ideal, or it's just a linear combination of the dpfi. And so, obviously, the zero set of dpH will always contain the zero set of dpf1. Okay, and so it follows. So another thing that one has for manifolds, obviously, is that you have the differential of the differential map between manifolds. So we also want to have, which is in a suitable sense at every point a linear map between the tangent spaces. So we want to have the same here. Still, I do it for fine varieties. So take X in the n, Y in the n. Let's see. Well, I could also say fine algebraic sets. Well, maybe I take the right. And phi, which I can write as f1 to fm from x to y, a morphism. We know that the morphism between affine varieties can be written like this, where these fi are actually polynomials. No? Morphisms are the same as polynomial maps. So the differential of phi at P is just the map given all the differentials. And so just I view this as linear polynomials, so they give me also a map from an to m. But I claim it is should I maybe have said that P is a point in X. But anyway, first I write this, so that P in X is this. And now so I leave to you as an exercise that if that DPP is a linear map from TP X to, which I call also DPP, to TP of P. Wow. So in other words, what we need, this is obviously in a map, we have to show that this maps TPX to TP to P of PY, and this you can see directly from the definition that this follows from the fact that this maps X to Y. It's an exercise in whether you can do simple computations with these things. And so the differential, so thus the differential that we want to, we consider DPP and TPX to TP of PY. So, so we have this linear map, and this actually, if this thing, if x and y would be non-singular and we are over the complex numbers, this actually is the differential as you consider it in differential geometry. Now one has the obvious things. So if you have an isomorphism, then it will send, it will give an isomorphism between the tangent spaces. So in particular, if you have an isomorphism between defined varieties, then it maps the singular points to the singular points and the non-singular points to the non-singular points. So remark, clearly, if I take the differential at the point P of the identity of X, so the map from X to itself, which is the identity, and this obviously is just the identity map on the tangent space of X. And you can check, using the usual chain rule of differentiation, that if I take the differential of the composition of two morphisms, this is equal to the composition of the differentials. No? So this is all just inventory calculus. So in particular, if P from X to Y is an isomorphism, and then dP phi from dPx to P of Py is an isomorphism. Vector spaces for all P in X. And so, so this is clear because the composition will be the identity, and so so if I take the inverse of phi, the composition of phi to the minus 1 will be the identity, and so the composition of the differentials will be the identity, and so they are inverse to each other. And so thus, in isomorphism, P from X to Y makes non-singular points so non-singular points and singular points for singular points. So in particular, if we look at, how was it? If we look at the classical qubit, we have this morphism. So this is the zero set of y squared minus x to the 3. This is not isomorphic. To A1, although we know there is a bijective morphism. There is bijective morphism. So t squared e to the 3 from A1 to this thing. But we know so because after all, so the point 0, 0 is a singular point, there can be no. We have already seen that this map is not an isomorphism, but we see also here that there is no isomorphism. They are not isomorphic. We can also see this so maybe I can just say also to look again at this example. Often, this is just a hint how one solves exercises. If a morphism, say, adjective morphism, is not an isomorphism, then the tangent space, or maybe I just say a surjective morphism, then either phi or EP phi for some p is not injective. So I'm not saying that if phi is bijective and the tangent map is injective, that it always has to be an isomorphism, but it's certainly the first thing you can check if you want to say that something is not an isomorphism. So for instance, this is an example, so in the above example, we have that if you take at the point 0, 0, the differential of t squared t to the 3, this is just 0. So the map is the 0 map, so it's certainly not injective. So another thing is that if x in y is a subvariety, you see this is correct? Yeah. Yeah. And then, by definition, so we are here in the end, the tangent space is contained in the tangent space of y. No, because here this is the 0 set of all the differentials of the elements in the I of y. This is the 0 set of all the elements in the ideal of x, all the differentials of elements in the ideal of x. And as x is smaller than y, the ideal is bigger. So thus, if the dimension of the tangent space of x is bigger than r for some r, then x cannot be isomorphic to a subvariety, subvariety of a non-singular variety of dimension r. So we can see that if the tangent space at some point is large, we will not be able to embed it into a smooth variety of dimensions smaller than the dimension of the tangent space. In particular, if the dimension of the tangent space at any point is bigger than r, then x cannot be a subvariety, not isomorphic to a subvariety of AR. Okay. So for this reason, it's some kind of obstruction to embedding it into smooth varieties. The dimension of the tangent space at P is also sometimes called the embedding dimension of X at P. So, because of this. Dimension of TPX is called the embedding dimension Okay, so you can somehow, so it gives us some kind of restriction of what can happen. Okay, so let's see. I think that was what I wanted to say about this. Yeah, so that was as much as we, in some sense, wanted to say about the affine case. For arbitrary varieties, we want to give an intrinsic definition of the tangent space. So one which doesn't have to do with the way how it's embedded into anything. And instead it's just in terms of the local ring at the point. And it's also, in some sense, more closely related to what you do in differential geometry. At least one of the definitions that one gives in differential geometry would be the same as this one. And so and it's also useful, I mean, for theoretical purposes, it's much more useful than this. So this is, we give an intrinsic definition of the tangent space X at P in terms of the local ring of X at P. So this also tells that it also only depends on any, so X is just a variety. So as the local ring of X at P is the same for any open neighborhood of P, it means that the tangent space of X at P and for any open neighborhood of P in X is the same. So it's a bit more abstract. So that so where X is a variety, P is an X, and MP in the local ring is the maximal ideal. These are all the functions in the local ring which vanish at P. So note that if I have an ideal, then I squared is I times I is just the ideal generated by all products of two elements, one from one ideal and one from the other. So we have MP squared is equal to the ideal generated by the set of all F times G, F and G are both in M. Yeah. So the tangent space of X at P is the following space. So we take NP modulo NP squared. Obviously, this is contained in MP, and then this will be this is obviously a K vector space. No, because already P is a K vector space, if we take it here. So in other words, these is a set of all linear maps from MP modulo MP squared to K, or if you wish, you can identify this with all the linear maps from MP to K such that, so maybe phi, such that phi restricted to fb squared is 0. No, making the obvious identification. So this is the tangent space. And so you do have, I don't know precisely how you define the tangent space in differential geometry, but one often takes, for instance, defines it as derivatives along curves or something. But anyway, so you can define it also in this form. So it is something which takes the differentiable functions which vanish at the point and sends them to k, to the ground field, whatever it is, C or R, wherever we are, modulo those which vanish to second order. So we take, so anyway, when you do these things, the differential, if you take it's a way of differentiating functions on x, and you do this by differentiating along curves, and you will see that this is determined by what happens to functions which vanish at p, and if the function vanishes to second order at p, it will give you 0, so it will give you the same thing. And one can also directly, in some books, you also find the tangent space to be defined precisely like this. Or it's a it was a long one. Maybe I can okay. So this is all. So then I just say the usual thing. So the point P in X is called a non-singular point. With the dimension of the tangent space is equal to the dimension of X, and otherwise singular. And as before, we have S drag is the set of all X non-singular points and X set of all P singular points. And as before, X is called non-singular if it's equal to its set of non-singular points. So now we want to show, we have now two different definitions of tangent space, and we should somehow see that they are the same. No? So at least for affine varieties, we have two different definitions, and we have to see that these are actually the same definition. It's also useful because if you want to actually compute the tangent space of an affine algebraic set, you would not find it maybe so easy with this definition because it's a bit abstract. No? You have to know what all the, what is the local ring of X at P. You have to find out how to do this, and then maybe that's not so easy. On the other hand, this is much more suitable for theoretical purposes and in many ways much nicer. So it's good to have both definitions, and they had better be the same. So we now, in some sense, sketch that the two definitions are the same. So if X in AN is an affine variety, want to see these definitions, these two definitions are the same. Obviously, that doesn't make complete sense because one is a subvector space of AN, and here we have this MP modulo M. They are not as sets the same, but we want to say that they are isomorphic vector spaces. So in order to do this, we want to show that these two different definitions of the tangent space are isomorphic. We have to give them different names so that we can compare them. So we write for the moment say small dx for our old definition of the tangent space. So a zero set of the differentials of the generators of the ideal, and large dpx for our new definition. Okay, then we want to see that these are isomorphic. So definition. So this requires a certain amount of computation, which I will not maybe do in all the details. So I have x is our variety, p in x, in n, and let say a equals to a1 to an be an element in our tangent space, the old definition. And we have to associate to it an element in this tangent space, so that is a linear map from MP to K, which vanishes on MP squared. So associate it a linear map which I write dA from MP to K, which, as I said, should vanish on MP squared. So which lies in this tangent. So I first have to, so this is again done in terms of differentials, I mean differentials of functions, but we have to generalize. We do not just do it for polynomials, we do it for eventually for rational functions. So first let if I have an element f, which is the class of a polynomial, namely x, then we put dpf to be d f dpf of a. Okay. So we have to see that this is well defined. So independent of the representative. So if f is equal to f prime, then f minus f prime lies in the ideal of x, thus dp, so yeah, of, I take f minus f prime of a is equal to 0, so that means dpf a is equal to dp f prime of So you see, for an element in this tangent space, small tpx, this does not depend on the representative. Obviously, if we are not in the tangent space tpx, it would depend. And we can extend this to the function field of x by the usual thing. You know, the function field of x is the fraction field of this, so elements of it are fractions of these classes. And we just apply the usual formula for the derivative of fractions. And then one would have to see that this makes sense. So for, maybe I just do it for elements in the local ring, for h equal to f divided by g in O xp, and A in the tangent space x at p, I mean the same A is here, we put, one has to remember the formula which I never can remember for the derivative of fractions, so dph of A is equal to dpf. What?
No.
Okay. Times g of t minus f of t times dg of A divided by g of t squared. And so this makes sense because we have the local ring of x at p, so this is non-zero, and so this is just the thing. Okay. So as a matter of fact, yeah, okay. And so I leave to you as an exercise that this, which is similar to what we already did, but obviously with slightly more work because one has to work with these stupid fractions. So exercise. This is well defined. So obviously you can write h as f divided by g in many ways, and then it should be independent of that. And it still satisfies the Leibniz rule. G and H are now elements in the local ring, and of A is equal to dt G of A times H of T plus G of T times dt H of T. Okay, so this is all just computation. And I, obviously, okay. Now with this, we can, if I can find it, so now with this we can finally define our isomorphism from the tangents from the old tangent space to the new tangent space. So in particular, if H is an element in MP squared, so then we know H as a sum or linear combination, as linear combination points. So H equal to sum MTH-AG, where both HI and GI are in the maximal ideal of P, no, because this MP squared is just generated by these elements, and so on the other hand, we see if we have a product of two elements in MP, we will get 0 by this state. So, but and if H and G are in MP, we have that dP of Hg is equal to dP f of A, H of A, times G of P, which is 0, plus H of P times dP G of A, and this is 0, so this is equal to 0. So we see that if H is MP squared, we have that dPH of A is equal to 0. So thus we get a linear map which I call dA from MP modulo MP squared. So it's a map from MP which vanishes on MP squared to K, which sends the class of F to dPF of A. Okay, so we just take the differential of any representative. So this is the map, and I claim that this and so also by definition the map which sends A to dA is a linear map, because this thing depends linearly on A. From dPA dx to dPx is a linear map. And then the theorem is that this is an isomorphism. So that X in the NBA closed subvariety and P a point in X, then this map delta from TP to TPX, which sends A to dA, is an isomorphism. Okay. So let's see. So first, we have to show that it's both injective and surjective. So the injectivity is quite easy. So we have to see that if dA is equal to 0, then we have to see that the corresponding A was the 0 vector. So that means I write A equals to A1 with n, with the components of the vector. So if dA is equal to 0, then dP f of A is equal to 0 for all f in the maximal ideal at P. This is what it means to be 0. That it gives you the 0 map. And so, in particular, put Ti to be, I take the ith coordinate in An minus its value at P. So in other words, if P is equal to P1 to Pn, it's just Pi. And I take its class in MP. So xi is a polynomial, so it's certainly a regular function. If I subtract its value at P is 0. And so it lies in the maximal ideal. I take its class. And so we have that dP Ti of A is equal to 0. But what is this? If I take dP Ti at A, I have to take the derivative of xi. So I have to take all the partial derivatives, the ith and multiply this with the corresponding component of A. So this is just the partial. Here only the ith partial derivative is non-zero because it's 1. And the corresponding component of A is AI. So this is just AI. So we have that AI is 0 for all I. That means A is equal to 0. So that's the injectivity. So we notice we can kind of single out the components of this vector by applying it to these. And for the surjectivity, we somehow want to use the same thing. We want to show that we can express the elements in MP modulo MP squared as linear combinations of these Ti. And then we will see that the map is projected. So, surjectivity so I take delta, the sum element in MP modulo MP squared dual. So I view this as a map from MP to K, which ranges MP squared, and we put AI equal to delta of Ti, where Ti are the same as these. And we had seen before that the AI is supposed to be the ith coordinate of the vector from which we have started here. So it's natural to say that we put A equal to the vector A1. So n. And we want to claim that our given delta is equal to this del A. Then we have proven this surjectivity. So by what we have seen, or by definition, we have delta of Ti is equal to dA of Ti. No? Because this was AI, we hadn't just seen this before. No? So you will want to show, so thus it is enough to show that T1 to Tn generate what is it, MP mod MP squared as a vector space. So if I have a linear map which coincides on generating sets, then they are equal. So let's do this in a few steps. So if I take an element f equal G mod H in MP, where G and H are elements in the coordinate ring of X, then if I take f minus G divided by H of P. So we replace H by just H of P. If you compute it, I hope I got it right, but you can also check. So this is G divided by H. And I think H of P minus H divided by H. And so I think it should be this. You can do the computation. And you can see, if I evaluate this at P, H of P is non-zero, and this is an element. So this is in AX, and obviously G of P is equal to 0. So this vanishes here. So this, I can write this out as G divided by H times H of P minus H divided by H of P. And both these elements lie in the maximal ideal. So this is an element in MP squared. So therefore, F and G divided by H of P are the same element in MP mod MP squared. So So therefore, we can assume, if we take a general element in MP, modulo MP squared, we can assume it's the class of an element in AX. So thus, MP modulo MP squared is generated by classes of elements in AX. And now so all elements in AX are polynomials in the TI. So by itself, an element in AX is the class of a polynomial in KX1 to XN. But obviously, I can, if I wish, shift the coordinates by the coordinates of P. So every element in AX is the class of a polynomial in the xi minus pi, and the class of a polynomial in these variables is the same as a polynomial in the classes. And so this is a polynomial in the Ti. And so if I take the product of two and a monomial in the Ti of degree bigger equal to 2 lies in MT squared, because Ti lies in MP. So thus we get that indeed MP over MT squared is generated as vector space by the Ti. And so the claim follows. We can also so I already overstayed my welcome. Okay, I will finish this by saying the last thing, because it's just an exercise. We have before talked about the differential of a morphism between fine varieties in terms of just the differentials of the coordinates. We can give a more intrinsical and more natural definition, which is also closer to what you do in differential geometry, namely following definition. Let P from x to y be a morphism of varieties, and P of point in x. The differential of phi at P is dp phi from Tpx to P of P. Why? Where we do the following. So we have a tangent vector now is a map from MP modulo MP squared to K. And what is the natural, if we're given such a map phi, what is the natural thing to do to get a map from this corresponding thing here is we compose with phi. So this is just mapped to V composed with phi. So phi sends the local ring at P of P. So if I have a function, so that means if I have a function f locally here, that's right. So that means f is mapped to no. So I have this thing, so the f lives here, so f yeah. So I have this map from we have this map so we first what? I'm a bit tired this morning, but okay. So we have a map from MP to MP squared, modulo MP squared to K. Now we if we take if we have a function here, if we compose it with phi, it becomes a map from here. So what this means is we have a function f which lies in M P of P. We compose it with phi, and then we apply V to it. So F is mapped to V of F composed with phi. Now, if F is a map here from M phi of P divided by M phi of P squared, if I compose it with phi, it becomes a map from here to K, and then we can take its, we can apply this linear form to it. No? So that's, in some sense, that's the standard thing. No? You define the differential of a map by taking the composition and applying the differential of a map to a function means you compose the function with the map and take the differential of that. And so that's what it means. And so then the exercise is that that this is the same definition as we had before. So the isomorphism so TPX to TPX that we just defined for X defined identifies this with our previous definition of the differential. So that in some sense, before we had written it in terms of the coordinates, but now we can see it is just this very natural thing. Now that the derivative of a function here is just obtained by composing the function with phi so that it becomes a function here and then taking its derivative here. Okay, so maybe that's enough. Thought that be long enough. We will see each other, I don't know, on Monday. I hope I did. So, okay, thanks.